Okay, so now we are ready to build some matrices. Okay, I'm going to tell you a transformation, and we are going to write the matrix that corresponds to this transformation, right? So this is how we do it. So remember that our rule was that the matrix A has as the different columns the transformation applied to the different unit vectors. So normally in 3D we use basis x hat, y hat, z hat. So this means that the matrix A associated to a certain transformation is written as 3 columns. The first column is the transformation applied to x hat. The second column is the transformation applied to y hat. And the third column is the transformation applied to z hat. Okay? So if I tell you a transformation, for example, I say rotation of the space by a certain axis. So what you can do is you can rotate your vectors x hat, y hat, z hat, and the results you place as the columns. Yeah? So let's see an actual real example. So let's consider a rotation of 90 degrees anti-clockwise. And now we are in 2 dimensions only. So we only have x hat and y hat. Okay? So what does this mean? So we have our 2-dimensional space with the x and y axis. So we have our x hat and our y hat. And then we want this transformation which rotates any vector 90 degrees anti-clockwise. So if we have, for example, this vector here, then we rotate it 90 degrees anti-clockwise. So we should end up with a vector like this, where this is 90 degrees. So this would be the transformed version of V. Yeah. So we want to find a matrix such that this transformed vector of V is equal to matrix A times vector V. That's our aim. Okay, so our aim is to find this matrix A. So we follow the recipe that I just told you. This matrix A will have 2 columns. The first column will be the transformation applied to x hat, and the second column will be the transformation applied to y hat. Why is this? Because that's how matrices are defined. The columns are the transformation applied to each of the basis vectors. Since we are in 2-dimensional space, our basis is x hat and y hat. By the way, in the problems, I don't usually say using the basis x hat, y hat, but if I was properly formal, I should do it. But let's say we understand each other, so whenever we are talking about 2D space, you use x hat, y hat. If you are talking about 3D space, we use x hat, y hat, z hat. Unless I explicitly tell you that we are using some other different basis. But normally, let's always assume we are using the basis of the x hat, y hat, and z hat. Okay, so let's start with this. So what's the transformed version? So we need to find these 2 columns. The first one is the transformed version of x hat. So what is the transformed version of x hat? So imagine we start with x hat, and we rotate it 90 degrees anti-clockwise. Yeah, so we end up with this. So this is the transformed version of x hat, which is actually equal to y hat. Yeah, so it's equal to the vector 0, 1. Yeah, that's the transformed version of x hat. Now, what is the transformed version of y hat? Which will be the second column. Yeah, so let's remember this first column, we already have it. This goes here. But now this second column, we need to find the transformed version of y hat. So what is going to be the transformed version of y hat? So we have y hat, we rotate it 90 degrees anti-clockwise, and we end up with what? We end up with this vector here, which will be the transformed version of y hat. And this is equal to minus x hat, right? Because it's pointing to the left. Therefore, written as a vector, this is the vector minus 1, 0, right? So this will be the vector that we need to use as the second column. That's as simple as it is, yeah? So finally, our matrix A is equal to 0, 1, minus 1, 0. And that is the matrix we were looking for. Let's see it in action, because I have this software that I was using for the videos that we can plug in any matrix we want and we can see how it affects the vectors. So let's go for it. So here we have a two-dimensional space where we have an arbitrary vector v, and I can move it with the mouse. Yeah. And then on the top left here, we have a matrix. So let's write the matrix that we just found. So the matrix was 0, minus 1, 1, 0. And I hit enter, bam. And now this code shows me what the transformed version of vector v looks like. And as you can see, this is a matrix which rotates vector v 90 degrees anti-clockwise, as we expected. Yeah? So no matter which vector I choose, I get this transformation. Excellent. Let's do another example. Let's do this second problem. We want the transformation, or we want the matrix associated with mirror reflection of two-dimensional vectors on the line y equals minus x. So first, let's draw what this looks like. So we have x and y. And the line, so we want a mirror reflection on the line y equals minus x. So what's the line y equals minus x? How does it look like? It looks like this. Crosses the origin and it has a slope of minus 1. Yeah? So this is the line y equals minus x. So what we want to do is a transformation which, when we have a vector, for example, vector v, the transformed version will be the mirror reflection of this vector, as if that y equals minus x line was a mirror. Yeah? So we would end up here. And this would be the transformed version of v. Okay? And we want to find the matrix that achieves this. So how do we find this matrix? We need two columns. The first column will be the transformation applied to x hat. That will be the first column. And the second column will be the transformation applied to y hat. So this is really easy, right? What's the transformation applied to x hat? So imagine your x hat vector, which is here. And now we reflect it through this mirror, which is this diagonal here. So the reflection looks like this, right? So we will get this reflected vector here. So this reflected vector is the transformed version of x hat, which is minus y hat. So we can write 0 minus 1. Now, what's the transformed version of y hat? So imagine you have y hat here. So now we do the mirror reflection on this line. Yeah? So if you place a mirror here, the reflection looks like this. Therefore, the reflection is this vector here. This is the mirror reflection of y hat. Yeah? Which is minus x hat. So we can write the vector minus 1, 0. And that's it. So now we can build our matrix with these two columns. So our matrix A is equal to 0, minus 1 as the first column and minus 1, 0 as the second column. Let's check it in our applet. So let's write down this matrix. It's 0, minus 1, minus 1, 0. Let's change this to minus 1. Bam. Now we have it. So is it working? Yes, it's working. Every vector is reflected along this line y equals minus x. In fact, we can have vectors on the other side, and it's always reflected, yeah? So it's working perfectly. This is our matrix for these type of reflections. So, another example. Let's get a bit more complicated now. Let's leave this for the next video. Thank you for watching.